Good afternoon, classes. This is Mr. Holmes. Today we're going to be talking about section 11-4 spheres. After this lesson, you'll be able to use Cavalieri's principle to show how the volume of a hemisphere is related to the volume of a cone and cylinder, and calculate volumes and surface areas of spheres and composite figures. So what I did first was, I drew half of a sphere, a hemisphere. It's not the best drawing. I drew it ahead of time. And I drew a cylinder with a cone inside it that I'm going to cut out. And what I'm going to do is I'm going to use these two figures, the half a sphere and the cylinder with a cone cut out, and derive the formula for volume of a sphere, showing the relationship. So what I did was drew the two pictures. Again, I'm not the best artist, so I had to draw this ahead of time to make sure I didn't mess up with anything. That's about as good as my art skills will be. So I draw half a sphere, and I'm going to have it have radius r, radius r, and my cylinder will also have radius r and height r. Therefore, these are basically the same height, even though it doesn't look like it. They're the same height. They both have the same height, radius r, or height r. The height of the cylinder is equal to the height of the sphere. And then for the cone I'm going to remove from the cylinder, and that's my cone. And for the cone removed from the cylinder, it's going to have radius h. Okay, so what I'm going to do is I'm going to figure out a cross-section area for each of these two figures. So what I did was I'm going to use this little cross-sectional area, this piece right here, and this piece. They're both going to have a height of h, this cross-section. So basically, if I start from the middle of the sphere and go straight up to this piece, this is going to have height h. We know the radius of the sphere is r. That goes from the center to a point on the sphere. That's radius r. So basically what I want to do is figure out the radius of the cross-section and then derive a formula for it. So notice this is a right triangle. So basically I'll just call this x for now. So x is what I want to figure out, the radius of this cross-sectional circle right here. And then I'm going to figure out the radius of this cross-sectional circle too. So right here we know that if x is my radius of my cross-section, I can write it in terms of r and h. So radius of the cross-section equals x. And since it's a right triangle, I know that the 2 legs squared equals the hypotenuse squared. So x squared plus h squared equals r squared. So what I'm going to do is solve for x in terms of r and h. So first thing, I get rid of the h squared, minusing it to the other side. So it becomes r squared minus h squared. And then to solve, I take the square root of each side, and I get x equals the square root of r squared minus h squared, all inside the square root. So that's the radius of the cross-section in terms of r and h. And we're going to come back to this in a minute. You're going to see where how this relates to the cylinder and the cone. So what I'm doing now for the cylinder and the cone is I'm going to figure out the cross-sectional area for each of these pieces. So we know the cylinder has radius r, and the cone has radius h. And even though it doesn't look, so the radius of the cone is equal to the height of the cone. Even though it doesn't look like it, they're both the same. Just not the best artist. So what I'm going to do first is figure out the area of the cylinder for this cross section. And the area of the cylinder is just, for the cross section, is just a circle. If it has radius r, it's just pi r squared, because the radius is r. For the area of the cone, it has radius h. So the cross section of this circle right here is just pi times h squared. So what I can do is I can take the area of the cylinder and then minus away the area of the cone. And if I do that, it becomes pi r squared minus pi h squared. Both pieces have a pi in common, so what I'm going to do is I'm going to factor that out and rewrite it. And when you do that, you're going to see it's very similar to over here. So it becomes pi r squared minus h squared. So that's the area of the cylinder minus cone. I found the radius here, but now I want to figure out the area of the cross section for the half sphere. I should have done that before. So the area of the cross section for the hemisphere is pi times my radius squared. So pi times this piece squared. When I square a square root, the square root just goes away, so I'm just left with pi times r squared minus h squared. So now you see that the area of the cross section of the hemisphere equals the area of the cylinder minus the area of the cone. So these two are equal. They have the same cross-sectional area at any height. And this is important because with Cavalieri's principle, remember, for two figures that have the same height and same cross-sectional area at any height, the volumes will be the same. So by C-A-V-A-L, Cavalieri's principle, the volumes will be the same. So in other words, the volume of the half sphere equals the volume of the cylinder minus the volume of the cone. So this is the same as the cylinder minus the cone. So the volume of the half sphere equals the volume of the cylinder minus the volume of the cone. So now I'm going to come up with the formula for volume of a half sphere and volume of a sphere. I know the volume of a cylinder with, in this case, the cylinder had radius r and height r, is pi r squared h. So volume of the cylinder is pi times the radius squared times the height. But remember, the height is just the radius in this case. So it's just r. So the height is r. So the volume of a cylinder is pi times r squared times r, which just simplifies to pi r cubed. And then the volume of the cone is 1/3 the volume of a cylinder. So this is just 1/3 pi r squared r. So remember, the cone is 1/3 the volume of the cylinder. This is just 1/3 pi r cubed. So now what I'm going to do is write the formula for volume of a half sphere in terms of these two. So if I combine like terms, really they both have pi r cubed. So really it's 1 pi r cubed, if you want to think of this, minus 1/3 pi r cubed. So really it's just 1 minus 1/3, which gives me 2/3 pi r cubed. And that's for a half sphere. So for a full sphere, it's just double. it's 2 times 2/3 pi r cubed. And this is just 2 times 2/3 is 4/3. So the volume of a full sphere, and this is your general formula, is 4/3 pi r cubed. So that's how you derive the formula for volume of a sphere, using the relationships between the half sphere and cylinder minus the cone. So it's a lot to derive, but that's where the formula comes from, rather than just accepting it as it is. That's how you can show that it's always 4/3 pi r cubed. When you get to higher level math, you can also use calculus to derive it. So volume of a full sphere is 4/3 pi r cubed. So cubing, remember, is multiplying the number by itself twice. So if the radius was 8, I do 8 times 8 times 8. And we'll get to some examples in a bit. So a couple other things. So that's the volume of a sphere. Surface area we're not going to derive, but I need to give you the formula for surface area of a sphere. Surface area, remember, just means how much to cover. So if I had like a ball, how much to cover the ball. So surface area is 4 pi r squared. That's the formula for surface area of a sphere. A couple other things. We talked about this before. Hemisphere is half a circle. Sorry, not half a circle, half a sphere. And the other thing is this thing called a great circle. A great circle divides a sphere into 2 hemispheres. So a great circle divides a sphere into 2 hemispheres. Remember, hemi is from the Greek, it means half. Thus, hemisphere means half sphere. So a great circle divides a sphere into 2 hemispheres, and I'll also add this for a great circle. It's the intersection of a sphere and a plane containing the center of the sphere. When you get to higher level math, you'll learn more about great circles. It's basically like a diameter of a 2D figure, like 3D, great circle. There's an infinite amount of great circles for any sphere. So those are the things you need to know now. So we know the formula for volume of a sphere, surface area of a sphere, and then hemisphere, great circle. So now we're going to do some examples. And I did post these on your page, so you can look at the examples we do. We're not going to do many, but we're going to pick and choose a couple. Okay, so we'll look at example 2 here. It says, what is the largest volume of a sphere can have if it is covered by 6 meters squared of fabric? So in this case, when you cover something, that's talking about surface area. So in this case, I know the surface area is 6 meters squared. Don't worry too much about the units. Remember, area is always 2 dimension, volume is 3 dimensions, so that's where the exponent of 2 and 3 comes from. So in this case, I'm going to have to figure out the volume given the surface area. So I have to do some working backwards. So remember, the formula for surface area is surface area equals 4 pi r squared. And I'm going to use the actual pi, so not rounded to 3.14, so the entire value. So in this case, I know surface area is 6, and then I set it equal to 4 pi r squared, and I solve for r. So to solve, I first divide by 4 pi, get rid of those. So 6 divided by 4 pi, let's do that. 6 divided by parentheses 4 times pi, close parentheses. I get 0.477464. I'll just write out a couple. I'll write out 0.477 equals r squared. And then what I do to solve for r, I just take the square root of both sides. So rather than rounding, I'll just leave this and then just press the square root button, and I get 0.69. So that's my radius of my sphere, 0.69 meters. So now, given that I have the radius, I now can use my volume formula, 4/3 pi r cubed, and solve for volume. So in this case, all I need is my volume, which I just figured out, substitute it in. So 4/3 pi r cubed. Order of operations, I do cube part first, so 0.69, y to the x 3, so to the third power. That gives me 0.328509 times pi, and then times 4/3. And I'll just do that as a fraction, 4/3. Or you can times it by 4 and divide by 3. And I'll get 1.376. And units would be meters cubed. So that is the largest volume. And it doesn't say what to round to, so I'll just stop right there. So that's the largest volume it could have. So given the surface area, you can work backwards and find the volume. Given the volume, you can work backwards and find the surface area. So you'll see a couple examples like that later on. So first example. Let's see now. Okay, let's look at these examples right here on the next page. What is the volume of a hemisphere with radius 3 feet? So remember, hemisphere means half a sphere. So what I can do is figure out the whole sphere and then just divide by 2 at the end. So remember, volume equals 4/3 pi r cubed. In this case, I'm given the radius, so I just substitute it in. And then evaluate. So 3 cubed is 27 times pi times 4/3. And I get 113.097. That's rounded to 113.1. But remember, that's for a full sphere. So for a hemisphere, I have to divide this by 2. So I get 56.55. So this is for a full sphere. But for a hemisphere, it's half. So remember, if it says hemisphere, you want half of it. So divide by 2 at the end. So it's 56.55. And it's feet cubed. And then for B, I'm not going to work out the entire thing, but really it's the same as part A, except here, diameter 13. So we don't need the diameter in our formula for volume. So to get the radius, I just take half the diameter, and that gives me 6.5 centimeters. And then I'll substitute 6.5 into my formula and do the same steps as above. And if you're curious to the answer, I'll give you the answer so you can have. So the answer for 3B is 575.17. That should be your final answer at the end. So you can work through it and just check to make sure it's 575.17. Okay, number 4. What is the volume of the space between the sphere and the cylinder? So I like these questions that deal with composite figures. So sometimes you're adding a volume, sometimes you're subtracting. When it says the space between, these are subtraction problems. So in this case, I have a cylinder, I have a sphere inside. Basically, I'm removing the sphere and figuring out what volume is left over if I just take out the sphere part. So I have to find the volume of both the cylinder and the sphere. So this is my formula, volume of the cylinder minus volume of the sphere. So let's start with the cylinder. The cylinder has a radius of 12. It's the same as the radius of the sphere. However, the height of the cylinder, I got to be careful. The height, if I go from my center straight up, that's 12, and it's also 12 down. So it's 2 radius, or it's basically the diameter of the sphere. So the height of the cylinder is 24. It's 2 radii. So formula for volume of a cylinder is pi r squared h. So pi times 12 squared times 24. And I'll just do that. So 12 squared is 144 times 24 times pi. That gives me 10,857.344. 10,857.344. And this is centimeters cubed. So I'm halfway done. Now for the volume of a sphere, we know the radius is 12. It's the same as the cylinder. So formula, 4/3 pi r cubed. 4/3 pi times 12 cubed. So 12 cubed is 1728 times pi times 4/3. 7,238.229. So to get the total area, I just take the 2 and I subtract them. So 10,857.344 minus 7,238.229. Let's do that. 10,857.344 minus 7,238.229 gives me an answer of 3,619.115 centimeters cubed. And it will say rounded to whatever number. If it's nearest tenth, it's 0.1. Whole number, 3,619. So that's how you go about solving questions given the composite figures if I want to find the shaded region. If the sphere was, say, on top of the cylinder, then I just add the 2 areas together. So you could see questions with like a sphere and 2 cones put together, questions like that. Okay, so we'll just look at a couple more and then we'll be done. So on the next page, let's see which ones we can look at. The error analysis. What is her error? Here. Surface area is, okay, Reagan's finding the volume of the sphere. So first, the surface area, that's not right. Surface area is 4 pi r squared, so this should really be volume. And then units. Volume is cubic units, so that's the error. When volume, you use cubic units, not square units. Surface area, you use square units, and it should be 4 pi r squared. So they have the correct formula, but they wrote surface area instead of volume, and the answer should be cubic, but their calculations are correct. Let's see, find the surface area, find the volume. Let's see which one we can look at. Let's look at number 9. Find the volume of the largest sphere that can fit entirely in the rectangular prism. So inside this figure, I need the largest sphere to do. So what is the largest radius I can fit inside the sphere? So if I use a diameter of 5, the height, then it's not going to be able to fit in the bottom because it's only 4 across. So the largest diameter I can use is 4. So the largest radius I can use is 2. So the largest sphere that can fit entirely in the rectangular will have a radius of 2. The dimensions of the bottom, because I can't do a 5 because it won't fit in the bottom, but I can do 4 if it fits entirely across. It won't take up the entire space up and down, but it will fit. So then I would just do volume equals 4/3 pi r cubed, which is 2 cubed, and then 2 cubed is 8, so it's just 8 times pi times 4/3, and that gives me 33.5. And the units are centimeters cubed. Okay. And if you're watching the entire video, I'm going to be doing a couple questions that will be on your assignment. So it works out that it pays to watch the entire video sometimes, which some of you don't like to watch, but it pays. So I'm going to look at number 18 right here. It says, find the area of each cross-section. So the cross-section just means this little circle. So this would be this circle here, this circle here, this circle here. So I basically need to figure out the radius of this. So I'm going to just call this x. And what I'm going to do is I'm going to write this in terms of r, h, and h1. So what I'm going to do is I'm going to use similar triangles. So basically I can do two triangles. I can do this big triangle and compare it to this tinier triangle. These two triangles are similar by AA. They have two angles in common. So I can use angle-angle similarity to show these two triangles are similar. So for the big triangle, I can use this side to this side. So for this side it's r, and this entire side is h plus h1. So r goes with h plus h1. This side goes with this side. And then for the smaller figure, the radius goes with the radius in this smaller triangle, which is just x. And then this side is just h1. So what I'm going to do is solve for x. And I just cross multiply. So this becomes r times h1 equals x times h plus h1. I'm going to solve for x. So to solve for x, I'm just going to divide by this piece, h plus h1 to each side. So x is just r times h1 over h plus h1. So that's the radius of this circle. So to get the area of the cross-section, it's just pi r squared. So I do pi times my radius, which is just x, so I write it in terms of this, squared. So this is my cross-sectional. So it looks very messy. So it's just pi times rh1 over h plus h1, all squared. So that's the area of the cross-section for that. I can use similar triangles for this. And the other two, you can use Pythagorean theorem to figure out the radius of the smaller circle. And this one, you are given the radius. It's r. So those two aren't too bad. Okay, 1920 we're not going to look at. 21 we're going to look at because it's good to know how to do one working backwards. So sphere with volume 35. So I know the formula is 4/3 pi r cubed. So to figure out the volume, to figure out the radius given the volume, we're going to work backwards. So I replace 35 with v, and I'm going to solve for r. So what I need to do is get rid of the 4/3 pi. So what I'm going to do is divide each piece by 4/3 pi. So what I do is 35 divided by parentheses 4/3 times pi, close parentheses. So 4/3 times pi is 4.188. So 35 divided by that, if I just hit enter, gives me 8.355. 557. That's what my radius cubed is. So to figure out the actual radius, I need to take the cubed root of each side. Because when it's squared, I do the square root. So cubed, I do the cubed root. So I take the cubed root of each side. And on the calculator, I just hit the cubed root button. That's second 0. Second 0. And that gives me 2.029. just say 2.03. To nearest tenth, it'd be 2. And now that I know what the radius is, I can figure out the surface area by using my formula given the radius. So that's how you figure out the radius given the volume. And then once you know the radius, then you can figure out the surface area. And then just real quick on 27 and 28 says find the volume of the composite figure to the nearest tenth. So in this one, you're just going to be adding all the figures. So this one is just composed of a cylinder and 2 hemispheres. Or if you think it's one sphere combined. So you can find each hemisphere, or you can just take both and combine them together. And the hemispheres have radius 5. The cylinder has radius 5 and height 6. And then I just use my formulas. And then for 28, I have a cone and a cylinder. For the cylinder, the radius is 10, the height is 12, and then for the cone, the radius is also 10, and the height is 10. Then I just find each, add them together. So that's how you go about composite figures. So this concludes the video on spheres. So we learned how to derive the formula for volume of a sphere using, using Cavalieri's principle. The area of a cross-section of a hemisphere is the same as the area of a cross-section of a cylinder with height equal to the radius minus the cross-section of a cone with height equal to the radius. So the hemisphere equals the cylinder minus the cone, and then I came up with the formula volume equals 4/3 pi r cubed. You also learned how to calculate volume and surface area of spheres and composite figures given the volume or the surface area or the radius or diameter. So again, this concludes the video on spheres, and now you'll apply it to your assignment and the real world examples. So this is Mr. Holmes signing out. Have a great rest of the day. Take care. Bye-bye.